Okay. We most finish all the material in these chapters. As I mentioned, two major knowledges you should keep in mind. There are several physical properties we teach, and there are several forces we teach in this class. So you just keep in mind two physical knowledge is a property first, and the force second. Okay, so but today I only focus on introduce about the shear force and the surface tension force. And most of the topic focus on the surface tension force, and we do several exercises to understand what are the nature phenomena in our life, okay, such as capillary and the needle floating and the bubble formations, okay. So the final one is very important property also is the vapor pressure, okay. So as you can see, I provided a certain definition of the vapor pressure, and our textbook, as usually we use the PV to indicate the vapor pressure, okay, and which is the pressure, the liquid phase and the vapor phase at the material will be in the thermal balance, okay. So the bottom figures I call that is the phase diagram. And you can see actually we have the diagram, the curvature line in here. And the type, the upper of this curved line, we call that is the liquid phase. And the beneath the curvature line, we call that the vapor, okay? So this is a very important curvatures we should try to understand by ourselves how it works for the vapor pressure. So if you consider there is the pressure will reach to the 100 kilopascals, so it's almost close to our 1 atm environment pressure we have, because the 1 atm is equal to 101.3 kilopascal, okay. And you can just based on this line to the right, and you will find out how the temperature, okay. The temperature in here is the 100 degrees. That indicates this is 100 degrees is our boil temperature in our life. Sometimes we cook the soup in our home, and that's because the environment pressure is the ambient pressure. So the boil temperature can reach to 100 degrees just based on this curvature line. But if we, in some cases, we go hiking, and we are on the mountain areas, so the elevation increase results the pressure decrease, okay? So when the pressure decrease, in case you can draw additional line, and you will have a different boil temperature, right? So if you lower than your ambient pressures, and in that case, your boil temperature will also decrease. And that's the reason why we cannot cook the soup on the mountain area if we didn't have another instrument to increase the pressure. If we don't increase the environment pressure, you cannot cook the soup at the mountains area. Okay, so that's the phase diagram is very useful for our understanding what the boil temperature we will have at the different pressure conditions. So, but what I want to say, this is also example, but we didn't need to calculate anything because I want to share some ideas. So the reason I put here because the vapor pressure is a very famous property to understand some engineering problems. Okay, so for my, I show one example in here. If we sometimes we have the pipe, and we can control a different flow velocity in the pipe. Okay, and right now I tell you based on the Bernoulli equations I just showing here. The Bernoulli equation tell us the idea is the high flow speed. Okay, if you have the highest flow speed, okay, and then you will have the lower pressure. Okay, the idea I write down here is just based on the Bernoulli equations, but in the following class, I will teach you the reason why the Bernoulli equations tell us the ideas. So that means if you are under the room conditions like the 20 degree, okay, right now it's a 20 degree, and at the 20 degree, you certainly know what the vapor pressure we will have. So the vapor pressure in here is equal to the 2.34 kilopascal. Okay, the vapor pressure is certainly at this number for the conditions of the 20 degree, like similar to right now. But if your flow speed is really high and result the lower temperature, so your environment pressure will decrease and will beneath the curvature, right? The point at this curvature line will move down because your environment pressure is changed. It's caused by the high speed flow velocity. Okay, so that means in that conditions, the liquid will change to the vapor. The liquid will change the phase to the vapor. Okay, and sometimes it will cause some problem because the vapor bubble is very terrible. Okay, so if you agree this idea, what is the idea we have? If the flow velocity is too high and the ambient pressure will going down. If in case the ambient pressure lower than the vapor pressure at this condition temperature, and you will have the phase change. The phase will change from the liquid to the vapor. Okay, so this is a very terrible idea, phenomena, because I show some photo in here. You can see there are some structure broken by the vapor bubbles. So this is the idea. There is a vapor bubbles were broken and erode the infrastructures of the hydraulic structures. Okay, so this is just the fan, and you can see some spillway. The boundary of the spillway also broken by the vapor bubble. So that's an engineering problem. If you design the different flow velocity, it's fine, because this the different flow velocity caused by the lower pressure, but lower pressure did not touch the vapor pressure. It's fine, because there is no phase change. But if you design relatively high flow velocity, your ambient pressure will touch the vapor pressure at these conditions, and then the phase liquid will change to the vapor, and the vapor bubble will broken the structure. So the engineers, based on their knowledge, they need to design the flow speed cannot higher than some threshold. If the flow speed higher than some threshold, the pressure will quite lower than the vapor pressure, and the liquid will become to the vapor bubble to broken some structures. Okay, so this is the idea for engineering. If the engineering know that the certain solution to solve these engineering problems, and they will design some limit for the flow velocity. And you can also see this phenomena, we call that the cavitation. The vapor bubble break the infrastructure, the phenomena, we call that the cavitation. Okay, so this is the very good example, and in the following class, we will see some example also caused by the Bernoulli, caused by the cavitation, and that's based on the idea of the Bernoulli equation. Okay, so this is almost our final slide, and the topic I write down in here, the title is the specific heat, and usually we use the C in our textbook, which is the energy, thermal energy associated with the molecules and in motion. So I just discussed if we have some specific heat to identify how large the energy required to molecule in motion, okay? And how can we have the different specific heat? So sometimes we can calculate the specific heat under constant volumes, and we call that the CV. The CV is the specific heat under the constant volumes. And another specific is with constant pressure. So we do some experiment under the constant pressure to measure how large of the specific heat. And we call that the CP. Okay. And in the previous class, I have teach you the ratio between the CP and CV. We call that the K, and which is the adiabatic exponent. Okay. So but in our teaching plan, we sometimes, because the thermal property are used for the gas problem. Okay. Which is the topic related to the chapter 12. So we don't touch more details about the thermal problem, especially for the gas material. So you just keep some ideas in your mind, and the specific heat usually will apply to discuss and understand some phenomena for the gas. Okay. So for the fluid, sometimes we did not. I mean, the fluid is liquid water or something liquid. We don't take into account for the specific heat in here. Okay, so we almost done the chapter 2, and in the next week we will move to the chapter 3. And in chapter 3, there are a lot of the problem related to the static problem, not the kinematic problem. So the static problem, we always do some force balance and to see what happens in solutions. Okay, and we call that the hydraulic static problem. Okay, so we may stop here